Alright, hi everyone. So thanks for coming to the talk. That question was a fantastic segue into this talk, which is about automatic labeling of point clouds for 3D object detection. So the main goal is that we want to get an auto labeling framework that can work for any LiDAR and is mainly with the focus of unsupervised domain adaptation. In other words, doing an auto labeling without any prior labels with that LiDAR that we want to label. So just a quick overview of this presentation. The first thing I'll cover is the framework that we use for auto labeling, and that's to generate labels for 3D object detection on any type of LiDAR. And the next is we have a short tutorial of how you can auto label your own point cloud data. So first I'll go through the framework of auto labeling. As everyone may or may not be familiar with, 3D object detection is quite a fundamental task for autonomous driving. So you use it in obstacle detection and path planning and so on. Typically, if you want to deploy a 3D detector on your own LiDAR, you would follow this pipeline of data collection, labeling, deployment, training and deployment. And it's basically your typical supervised training of large amounts of data on your specific sensor setup. And so, as we all know, data labeling is very time-consuming and expensive. So one way of addressing this cost is to use this thing called auto labeling. And it's, in other words, another way of calling it is also self-training. And the idea behind this is to generate predictions for unlabeled data with large offline models. And then you can refine these predictions with tracking and supplementary machine learning models. And once you have these refined predictions, you can then use them as pseudo-labels for training your own data on your own unlabeled data that you collect. So this is a popular auto labeling framework from Waymo, presented in CVPR 2021. So the main idea behind this is you have your offline 3D detectors, and these are typically like your larger scale 3D detectors. Once you get a few detections, then you do multi-object tracking. And then what they do is they split their tracks into static and dynamic objects, and then they'll treat them separately. One of the reasons why is because the static objects for point clouds, if you drive past an object, you can actually accumulate a lot of different observations, and therefore you have a much denser observation of the object. So what they use for this refinement process is they use a separate machine learning network that's based on PointNet. And so they train this network in a supervised manner, which basically you take in multiple temporal predictions, and then you refine the output for the current frame that you want to label. So you can classify this kind of work as a semi-supervised 3D object detection, and basically the idea is to improve your object detection with a mix of labeled and unlabeled data. In this kind of approach, you have access to labeled data for your particular sensor setup, and what that means is that you have a really strong baseline 3D object detection, and when you have strong detection, you then have strong 3D tracking. And what you can also do is you can then use your supervised models for offline box refinement, because Waymo already has so much labeled data that they can do that for their label refinement. But consider this application. Say you previously trained a detector for a 32-beam LiDAR, and now you're upgrading to a 64-beam LiDAR. And this could be any type of upgrade that you do. It may not be this case. Or maybe you were wondering if you could take like a new scenes trained detector and you just directly deploy it to your 64-beam LiDAR. Right, so this is the situation that we're looking at. And you might see something like this when you actually try it. So this one here, this point cloud is from Waymo, and it's a 64-beam point cloud. So we took the new scenes trained voxel RCNN detector and we directly tested it. And you can actually see that in the far range detections up top here, there's a lot of missing detections, even though you can actually quite clearly see a lot of these pedestrians and vehicles. And so this brings us to the actual topic of cross-domain 3D object detection. So if you were to test and train a model on the same data, if you were to have a Waymo detector and you test it on the Waymo data, this is the accuracy you get for all the different ranges in the blue bar graph. If you then took the new scenes trained detector and you tested it directly, your performance drops significantly. So you can see that it kind of drops, especially at further ranges from 30 to 80 meters, you're basically getting nothing. And that's reflected directly in this GIF that you see over here. So what we see here for cross-domain object detection is that they generally have poor generalization to different LiDAR types. And what that looks like is you have a lot of missing detections, false positives, and also misaligned confidence scores. And that's really important because you can't just easily say, all right, this detector has 0.6 confidence, I'm pretty sure the box is good. It doesn't always work like that. And we assume in this case that you don't have any existing labels for your new LiDAR, and so that puts us into the category of unsupervised domain adaptation works. So we also notice that this actually happens to a lot of different detectors and across different LiDARs. And one of the reasons for this is because there's a large difference between your training and your testing data, in other words, the domain gap. And so this could happen because your scan patterns are different or your geography is different. For example, there's a popular paper that says that if you take a Waymo detector and you test it on key, it actually fails a lot of the times because it's not that it can't detect the cars, but that the cars in European countries are very small. So then you end up having a lot of missed detections because your object size estimation is too large. And so it doesn't meet the IOU threshold. And then the last one is whether artifacts in different LiDARs can look quite different. And so what we notice from this is that actually scan pattern is the largest contributor to the drop in performance. And in certain cases, it can be up to minus 90% for some classes. And this is quite different to image where the pixels are quite structured in a grid-like fashion. So why does the performance drop, you might be wondering. In this case, if you look at the image on the top left, if we took a new scenes trained detector and we just tested it on Waymo, as I showed earlier, you may have really dense observations of pedestrians and vehicles, but you can't really detect it in this detector. And the reason being is that you don't have pedestrians or cars that look like that in the new scenes dataset. For the second case, I'm not sure if you can see, but in the bottom where we circled in the red, that's actually the LiDAR reflected off the ground because there's a puddle there. And so you can see the vehicle is kind of reflected across the ground axis. And this looks very different across different LiDARs, and that could also be a reason why this lift detector couldn't detect anything on the Waymo dataset. Next up, if you're trying to deploy a Waymo trained detector on a sparse LiDAR, like the new scenes, you can actually see that it does identify that there's a car there, but it's really hard to place the height of the car when you've only got a single point cloud ring. And so that's quite challenging. And then in the bottom right, you can see that for the lift dataset, they don't do ego motion computation. And so that's really challenging if you took a detector that was trained on lift and you tried to test it on something else. It may get a lot of different artifacts, or in this case, if you test a Waymo detector on lift, how do you evaluate it? Because do you define the boxes to include the entire thing or to leave out only part of it? That's the later part of the point cloud. So then we come back to this auto labeling framework, and we realize that we actually have really poor 3D-based object detection as a baseline. And when you have unreliable scores and you have a lot of missing detections, you can't get good tracking either. And then when you don't have you don't have labels for your LiDAR, how do you actually get supervised refinement networks for refining these boxes? So our goal here is then to get object detection auto labeling for any type of LiDAR. And the idea behind this is for transfer learning, so that you can label your own LiDAR and basically fine-tune these detectors to get good performance on your LiDARs. So our solution that we propose is called multi-source 3D, and the main idea is unsupervised auto labeling. And so I'll step through this first. The key concepts behind this, there's mainly two. The first idea is to take a lot of different pre-trained models that are trained on different source data sets, such as new scenes or lift, in order to label your LiDAR. And that's different to a lot of the existing works that just take a single detector to generate labels. And then once you have a bunch of these labels, then we refine them temporally in order to make sure that they're consistent across your entire sequence. So I'll go through the first part first. In order to actually refine labels, what we want to first achieve is to get a high label recall. We don't want to miss any objects. And so we try and get as much region proposals as possible in this step. So if you took a detector trained on lift and you tested it on Waymo, you may have something that looks a bit like this, where you miss a lot of cars. So the idea behind using multiple sources is that when you have detectors that are trained on different source data sets, they might pick up something that another pre-trained detector missed. And so you see here, we created an ensemble of different detectors trained on different source data sets. And then we also came up with box fusion that estimates a density function for each box parameter, and we basically take the majority vote of what they think that parameter is, for example, the heading or the centroid. And so in the bottom left, you can see that this helps us to be able to get better box localization, and it also helps to filter out the detections that were not a majority. So then it begs the question then, what kind of pre-trained detectors do you include in your ensemble? Because there's so much flexibility here. And so we dig into this question a bit, and we look at this idea of multi-frame pre-trained object detection. So I don't know how many of you guys might be familiar with the new scenes benchmarks for 3D object detection, but basically the new scenes dataset kind of pioneered this idea of having a multi-frame point cloud where you attach a whole bunch of historical point clouds to your current frame. And the idea is to use the localization to transform the previous point clouds into your current frame's coordinate frame. So what we find in the benchmarks for these new scenes trained detectors is that it can give up to like a 10 average precision boost just simply using multi-frame point clouds compared to a single frame. And so when you accumulate all these different point clouds, you then attach a timestamp to it so that the detector knows which points to detect for. We find that this actually generalizes pretty decently to different LiDARs as well. If you took a new scenes detector and, for example, if you had a new scenes detector trained on just a single frame and you tested it on Waymo, your performance is a lot lower than if you just took a multi-frame new scenes detector and you tested it on Waymo. And the reason for this is because when you accumulate frames in new scenes, you actually have vehicles that look quite similar to what a vehicle may look like in the Waymo 64 beam LiDAR. And we also find that, interestingly, it works the other way as well. If you accumulate frames in Waymo, even though it's super dense compared to accumulating frames in new scenes, it also helps to identify objects slightly better in the new scenes in sparse LiDARs as well. So, based on this finding, we therefore use 3D detectors that are trained on multi-frame point clouds to improve the domain generalization to different types of LiDARs. And then we wonder, like, are there 3D detector architectures that are actually domain generalizable? So we tested a whole bunch of different detectors that are like point voxel or just voxel based, and we found out that they're actually all kind of similar in how much they drop in their performance. If you look at these box plots, they're not very varied at all. Most of them drop by a similar amount. And so what we actually find is that the detector's performance on the target domain on your specific LiDAR is actually more correlated by the degree of similarity between what they were trained on and what you're trying to deploy it and test it on. And so the idea behind this is that we want to include detectors that are trained on different sources for better domain generalization to the LiDAR that we want to label. So once we have our fuse boxes, then we move into the tracking part of it, and this is straightforward. You basically assign the tracking ID to each box. And once we have that, then we move into temporal refinement, and we make an effort here to do this without any supervised learning because we don't have labels for the LiDAR that we want to label. So moving into the first component of this, we call this retroactive object labeling. And the main idea is that you may be able to identify that there is an object, but you may not exactly know what that is. And so I don't know how many of you can actually tell what this is, but it's if we look at it move a bit, you can see over time there actually is a pedestrian. And so what you can do once you know what it is you can propagate that label back in time to when you first observed it, and you can use that to basically auto-label the entire track that you have. And so it's similar to human perception where you see an object but you don't really know what it is. And once you actually do confirm what it is, then you can then use that label to kind of associate it with all the times that you saw it in the past and in the future. So we do this for both pedestrians and vehicles. So next we focus on static vehicles. And the reason why we focus on static vehicles is because pre-trained detectors can be quite unreliable. So they're unreliable in terms of their confidence scores and also whether they can actually detect the car. And the reason why we use parked vehicles is because as you drive through an entire sequence, there are different observations for different objects in the scene. And so as you have different perspectives, you can be able to detect the vehicle at certain times, whereas other times you couldn't. So what we then do is that for static vehicles, because they tend to remain stationary, we can then use a few confident detections to then propagate them into the past and into the future. And this allows us to get good far-range labels that can improve our detector's range. Also, we can then use all the temporal detections in that sequence and fuse them with our KDE box fusion that we showed earlier. And we can refine all that for just the frame that we want to label. And finally, because vehicles are rigid body objects, so if you have accurate static vehicle labels, it actually also helps the detector to generalize to dynamic vehicles as well. Next up, we look at the pedestrian refinement. So for pedestrians, if you take a pre-trained detector and you test it on your LiDAR, what we found is that a lot of these detections tend to be false positive pole-like objects. And so it's quite hard to tell apart poles from pedestrians because a lot of times when I look at the point cloud as well, I can't really tell them apart. And the confidence scores don't really help either since they mostly fall around a similar range. Sometimes they're super confident, but then when you look at the image, it turns out to be a pole. So there is one clear distinction though that we use for refinement is that poles can't move, but pedestrians can. And so what we start off with is that in order to get true positive pedestrian labels, we look at pedestrian tracks that are actually moving. And so this is what we focus on for the pedestrians first, and it actually really helps with static pedestrians later on because dynamic pedestrians are not always moving. Throughout a sequence, they walk and they stop, and they wait for traffic lights or something like that. And also, if you do multiple rounds of label refinement, which I'll talk about in the next slide, it can actually improve the overall detection of stationary pedestrians as well. So this part is what we call the iterative label refinement. So we've defined our auto labeling framework, but the idea behind this is to take the detector ensemble, get a general bunch of detections and auto label the dataset once, and use that to train a few models. If you can train maybe about 2 to 3 or 4 or more, you can use these models to then regenerate the labels and refine your initial label set. And what this helps with is that initially you may be able to get, you might miss a few pedestrians here and there, you might miss a few vehicles here and there, but your retrained models typically are able to detect them. And they also tend to have better prediction and confidence score alignment, which means that it's much easier to threshold the confidence and get better boxes in terms of localization and actual class prediction. And so the main strategy for this is that we follow like a strict strategy for the first few rounds because we don't want to introduce too many false positives. It might look more perfect to have like a lower threshold and just have a lot more labels in the scene, but it's really hard to get rid of false positives once the detector has learnt it. And if you do this iterative label refinement kind of strategy, every time the detector will constantly detect these false positives with a very high accuracy. And once that happens, it's really hard to remove that down the road. So I'm sure you guys are all wondering at this stage, like, how does it actually perform? Right, so if you train 3D detectors with our automatically generated labels, we show that we can obtain state-of-the-art results for unsupervised domain adaptation. And just to talk through this table a bit, this one here is basically taking the off-the-shelf detector. In this case, we have a lived pre-trained detector and we test it on the 64-beam Waymo dataset. So that's the starting baseline performance. We show that we can obtain quite a decent boost in performance by around over plus 10 average precision for both vehicle and pedestrian classes. And we also show that if you look at so this part here is if you train it with human annotated labels, which is the GT train, and we show that in the bird's eye view average precision, we can obtain quite a similar performance for vehicle detection. We also argue that for the purposes of autonomous driving, bird's eye view detection is mostly sufficient for downstream tasks. And this one here we show the auto labeling of the new scenes dataset, which is a 32-beam LiDAR. And we show that this is the starting performance of just taking an off-the-shelf Waymo detector and testing it. This one here is our auto label result, and this one here is training with human annotated labels. And likewise, we also show that we can obtain quite a similar performance to the bird's eye view detection for the vehicles. And we also outperform all the existing works in this field. So in terms of the iterative label refinement, the main strength for this iterative label refinement is that we increase recall with each round while maintaining precision. So if you look at the delta here, the delta compares the 4th round and the 1st round. And we show that especially for the 30 to 50 meters range for the vehicle, we can increase the recall quite a lot for further range vehicles while still maintaining our precision. It's a small drop. And in terms of the pedestrian, it's quite a large improvement in recall. And this is really good in increasing the data variation that we feed to the model without introducing too many false positives. In terms of the retrained detector's performance, we show that for each round, we can generally boost the performance by quite a bit, and you see a large jump as well in the pedestrians. So here are some results of what the performance is like. On the left, we show the off-the-shelf performance of a new scenes detector on Waymo point clouds, which we showed earlier. And on the right, we show if you auto-label these 64-beam point clouds and you train the model, you can get quite a good amount of far-range detections. And what you can't see is that the confidence scores for each of these boxes are also a lot more aligned with how good the actual box prediction is. The next one here we show is a 32-beam LiDAR. If you took a Waymo detector and tested it on the new scenes point cloud, you'll end up having a lot of missing detections for these pedestrians. And they're quite dense pedestrians as well, but you never see pedestrians like this in Waymo. And on the other hand, for us here, we're able to detect all these pedestrians, and we also don't have false positives like we have less false positives, sorry. For example, we don't detect this road divider over here as well. So that's in general for this presentation of the auto-labeling framework. You can read our paper for more information. We go into a lot of detail about why 3D detectors suffer from all these problems, and we also give a lot of quantitative results for the different issues that we find in domain transfer of all these detectors to different LiDARs. So the next part of this is a tutorial. Feel free to scan this to take a look at our Jupyter notebook. So we'll go through this tutorial to talk about how we collected our own data and we auto-labeled it, and we'll show a performance of our 3D detector at the end of this tutorial as well. So feel free to take some time to scan this if you want to follow along. So for this part, I've basically screenshotted the parts of the Jupyter notebook and just copy-pasted it in to make it easier, but you can have it for your reference. So what we show in this tutorial is that we collected some data in the University of Sydney campus. We used an ouster 128 beam, the OS1, and we also used an open source LiDAR odometry called KISS-ICP from the University of Bonn to generate some the localization. And we provide links to download this mini 100-frame point cloud dataset as well in the tutorial. So just a quick code breakdown. We mainly break this into 4 pieces. The first is just a bash script that can generate a whole bunch of predictions from different models. And then we have 3 main Python files that fuse all the detections, generate the tracks, and then also we refine the tracks, including the last part where we do the non-maximum suppression, the pseudo-label filtering. So for this tutorial, we just import the key functions just to give a general idea. So for this part, we show how we can load in a whole bunch of different pre-trained models up the top here, and then we can generate a whole bunch of predictions based on these models. So we run a bunch of different test time augmentations settings, and we also change the number of sweeps used at inference for this data set. And the reason being is that we want to try and increase the chances of matching what the detector has led with the LiDAR that we are using and the potential scan pattern that may match. So if you look at the bottom here, for 100 frames, we have 12 detection sets just for 2 pre-trained models. And the total number of boxes for, like, say, the 0 frame is around over 1,000. So what that looks like is you can visualize this here, and we also show this in our notebook. It's interactive, which is great. We find that when you ensemble a whole bunch of different detectors, you can, in general, increase the domain generalization and performance to different LiDAR types. And you can also change the types of pre-trained models that you put in this ensemble to increase your domain generalization more. We find that there's higher recall in general for far range and occluded objects. And also, if you just use a single detector, you might end up getting a whole lot of false positives or like pretty badly localized boxes. Like if you see this one here, some of the sparse cars are not very well localized. And so you can weed out all these little false positives there. So the next part is once we have all those predictions, we then fuse the predictions using KBF. And we basically match all the boxes based on the radius to the center of the box. And once we have that, it's just one line in this bottom here. So that looks a little something like this. And in general, when you fuse all the boxes with KBF, we have better object localization, and we also discard a lot of the one-off bad predictions here and there. And this is especially useful for further range and occluded objects as well. So the next part, this one's straightforward, where you generate track IDs for each object, and we generate 3 sets of tracks here. We generate one for all the vehicles in the frame, and we generate one for the static vehicles only, which we use a stricter IOU matching, and the last one we generate tracks for pedestrians. So the refinement stage, this one contains retroactive labeling and the static vehicle and pedestrian refinement. Then once we do all the refining, we project all the fused boxes and tracks and refined boxes into each frame, and we just use non-maximum suppression filtering. That looks a little something like this, where initially your labels may have a lot of false positives or might combine 2 pedestrians into one, but then once you refine them with the tracks, you get a lot better localization and positioning of these boxes, especially for far range and occluded vehicles. You also have reduced false positives, and we adjust the confidence scores for the refined boxes as well. So with the iterative label refinement, we also use strict thresholds for the first round, as we mentioned before, because it's hard to filter out the false positives. And this here is a 3D detector that was trained with our ouster point clouds that were auto-labeled from this framework. And you can see here in Sydney CBD, there's a lot of pedestrians, and I think the detection is pretty good. Yeah. Cool, so that's it for this presentation. You can read our paper to find out more, or you can visit our GitHub where we have quite an extensive documentation. Yeah, and just feel free to ask any questions. Stop me later on if you do. So we do have time for questions now. If there's any questions, feel free to ask. Yeah.
I asked during the first part of the presentation, you were talking about retroactive labeling. And my question is, until what frame in the past should we propagate a label? I mean, there is a certain time window when you can tell that it's a pedestrian, but it's not the same if you go backwards.
Yep. That's a bit of a, it's more of a heuristic where sometimes if you just, what I had to do when I auto-labeled a lot of these is I had to visually assess a lot of the tracks and a lot of the propagation. So sometimes if you propagate it too far, you end up getting too many false positives. And so the main idea is not to propagate it too far, but just like the neighboring frames that it may have missed, and like the occluded frames here and there, or the frames, because initially when it detects the object, it may not be that strong. But what we do is we assign like a low score threshold for tracking so that we can keep an eye on the object even though the confidence score is quite low. And so in that case, we actually do have a pretty decent localization, especially for pedestrians, because say for, just to give an example, for vehicles, if you were to track vehicles, it might actually be hard to get the heading right for vehicles. But for pedestrians, if you can detect one that's moving, generally the localization is it just might rotate on the spot. It's not too bad, but it'll still generally follow the pedestrian if it's tracking it. So we find that for pedestrians it's not too bad, but for vehicles, especially static vehicles, you may not want to propagate it too far because it might just be a vehicle that stopped at the traffic light and then driving off. Yeah, does that answer the question?
Yeah, sure. So just to give like the overall idea, do you have like a certain fixed number? Let's say 5 frames to the past for pedestrians and for vehicles, and they move faster, it's perhaps 10 frames or I don't know. Something like that, it's like by the concept?
Yep, we do have some defaults, but it's not really based on the speed because the speed is more of a tracker problem. And if you collect your data at 10 Hertz, we set up some pretty decent defaults to be able to track objects like pedestrians and vehicles at 10 Hertz. In terms of the label propagation to the future and the past, that's based on your data and how good the pre-trained detectors will work on your particular LiDAR.
Okay, thank you so much.
So,
I have a question about multi-frame point clouds, and especially what can be the effect of more moving vehicles or moving pedestrians during capture, because like, I suppose you
not necessary, but thank you. I suppose you use it mostly for stationary vehicles so that you can observe it from different observation points. But like if in those multiple clouds you have moving objects, you're going to get like sort of a trail. Does it have like a bad effect on your precision and recall?
So there's a paper out by Waymo where they did a quantitative study on this, and they showed that if you accumulate up to 4 frames for both static and dynamic objects, you can actually get quite a decent performance boost. The more you accumulate past that, the static vehicles will benefit, the static and slow vehicles benefit, but the dynamic vehicles start to degrade in performance. And that's because of the motion tails. A lot of the motion tails start to overlap, or it starts to make it a whole lot more confusing to detect. And so what we find in the multi-frame is that generally for most data sets, when they do this accumulation, we find like a 0.4 seconds of historical data is a good general rule of thumb to use, where you can get a decent performance boost without too much of a degradation. And we find that it actually works pretty well for dynamic vehicles and pedestrians as well, because say for the new scenes data set, if you just use a single frame, it's hard to tell that a pedestrian is there. But if you can see like say 2 rings and the 2 rings are kind of moving like that, just for 4 frames or 10 frames in new scenes, then you can actually tell the presence of a pedestrian, even though it's sparse LiDAR. Yeah.
Okay, thank you.
Yeah, one question regarding this using ensembles to detect various characteristics of different data sets. That makes a lot of sense to me. What I'm wondering is, if you look at the aggregation of those, how do you decide whether it's actually a false positive?
So in order to minimize the false positives, we use the static vehicles to do that, mainly because we know that the static vehicles are there. And if we drive past and they constantly agree on that position, then we can use that to minimize the false positives. So that's why in terms of just, like, we don't just use one-off predictions typically. We make sure that it's temporally consistent, and that's how we filter out the false positives. Yeah. There's also another mechanism where we discard any predictions that don't have a lot of overlapping ones in the ensemble. So we set a default of 3 or 4, such that there has to be at least 3 or 4 detectors that agree in order for us to actually fuse it. Yeah.
Thank you.
So can you give us an estimation of what's the maximum relative velocity for the moving object?
I don't know if I have those numbers for you.
I mean, for the moving objects, what would be the maximum velocity that you can detect using this method? I mean, have you tried highways with high relative velocity?
Are you talking about what's the maximum velocity that I can auto label, or that the 3D detector can?
Maximum velocity between the ego vehicle that you're collecting data from and also the vehicle that you're detecting. For example, if the vehicle pass from the ego vehicle with a velocity of, I don't know, 100 kph, can you detect it and track it properly with this?
Yep. So in terms of the auto labeling, that's more the question of how well the 3D detector works. In that case, I don't know if it's a single static frame. It doesn't really matter too much if the vehicle's moving fast, because you can get the observations as fixed and just use a single frame detection.
Because you are collecting the data. I mean, you are moving the data from past and collect them, accumulate them basically. Yeah?
Yes, but I only do that for static vehicles, or pedestrians don't typically run in the data sets. They're usually mostly walking. Yeah. There is something to be said about the speed of the ego vehicle though, because this method uses localization. In other words, you need good localization to be able to make sure that the static vehicle isn't jittering in its actual position, because otherwise when you propagate the boxes back in the past or the future, it might be slightly off. And sometimes, especially if your observation is quite sparse, sometimes the box is here and the points are here, but then if your localization is off, then the points will be slightly outside the box. And what you end up having is maybe more of the ground points or something like that, and that's really quite detrimental as well.